from Chulalongkorn University of Thailand.
Okay. Yeah, thank you. So I hope you still continue to awake, right? We already have 3 presentations, and this is another 3 before you are taking a break. Yeah, so welcome to the ICT for Secure and Smart Community session. Yeah, and again, the presenter would have 12 minutes for presentation, right? And then 7 minutes, 5 minutes, right, for the question. Yeah, so let's welcome the first presenter, yeah, Dr. Nachapong Hati from NICT. Yeah, the presentation is Smart Energy Sharing and Management Devices for a Low Carbon Society. Yeah.
Thank you. Thank you for your kind introduction, and good morning, everyone, because you're just waking up, I assume. And my name is Nachapong Hati from NICT, Thailand. My expertise is in power electronics. And for the background of the project, some areas in Thailand and possibly also in some other ASEAN countries cannot access national grid. In Thailand, many of these regions have been designated as reserve forests, where the public utilities are not allowed, including national grids. From the left side, you can see that the location of the target school of our ongoing project. The school is in a community within reserve forest in northern Thailand. The energy resource of school and energy and community are micro hydro power systems and PV power systems. For the micro hydro power systems, they have a limited water capacity, so the power will be very fluctuation and shortage. But for today, I won't go into the details of the micro hydro power system. And for the PV power system used by the school, this picture shows the PV system installed on the school rooftops. There are at least 7 independent PV systems. For the simplicity, the right side picture shows only 2 systems. Each system contains PV panels, PV charger, PV inverter, 48-volt battery, and electrical load. The benefits of using independent off-grid power system is that it's safe because each system operates with low voltage battery, and the inverters and other devices are widely available on the market, allowing local technicians to maintain this system with ease. However, the main issue is that the energy cannot be shared across the system. While some systems may produce excess energy and others experience shortages, resulting in high energy waste, low reliability, and inefficient energy use. This project aims to solve these challenges by introducing ESDs or energy sharing device, which I will explain later. Before diving into the details of energy sharing devices or ESD, let me outline our current progress of our ongoing project. We have developed and installed the first version of ESDs at the school, and the teachers have been trained to operate the devices as shown in the pictures. For the next target will be gathering utilization data of ESD for overall improvement for the next project. Then propose a new project. In the new project, the works will be to promote the use of ESD in some other communities, maybe in Thailand or and our ASEAN countries, and improving the packaging of the ESD. From the picture, you can see that the size of the ESD now is a little bit huge because we use a standard electrical enclosure. And for the IoT function, in the case that we equip the IoT function, we can monitor the operating of the ESD online and can adjust the energy management plan easily. And for the next one is to develop the advanced energy management board, which I will explain later. And the target number 3 is to collaborate with universities and partners in Thailand, also in ASEAN countries, for further research, development, and student internships. For the main proposed method, energy sharing devices, first of all, I would like to acknowledge that this ongoing project is financially supported by the Office of the Regulatory Commission, or ERC, Thailand, from December 2022 to December 2024. For the proposed project, the question is why ESDs? The answer is that because they do not affect the operations or reduce key advantage of the original system, which I have mentioned before. There are 2 types of ESDs, as highlighted in orange in the left side picture. For the first one is the DC to DC type. This one is for sharing the energy directly between batteries of the systems. This type offers the bidirectional power flows, allowing the energy to move between batteries in either direction, can move forward and backward. It's good for the system with close proximity batteries. For the AC to DC type, is for sharing energy from AC lines, such as maybe from micro hydropower system or from the other inverters from the other system to charge the battery. In this case, the power can flow only in one direction, from AC side to DC side or to the battery. This one is suitable for the system that's located farther apart. In practice, either or both ESD can be used depending on the system configuration. We don't need to select all of them. And this slide shows deeper into the details of the ESD. For the DC to DC type, we use dual active bridge power converter to share the energy between batteries. The power can flow in either direction, such as from left to right or right to left, like this. And for the AC to DC type, we use the boost converter here at the AC side for improving the power factor. And we use the dual active bridge converter to charge the battery. Both of them have the digital control that can control the overall system and can communicate to other devices, especially to the BMS of the battery module. BMS is battery is the battery management system. For the top right picture shows the prototype ESDs in use at the school. There are 5 independent off-grid PV systems. System number 1, 2, 3, 4, and 5. For system number 1, 2, and 3, they are close together. So we use DC to DC ESD to share the energy among the systems, as highlighted in green. For the system number 4 and 5, because they are located farther apart, So we use AC to DC ESD to share the energy over the AC line. Another solution for this project on the left side, we also developed the simple energy management boards. This one is for EMB. This one is for enhance the energy sharing efficiency. It can be used with the AC to DC ESD in this project, and also can be used with the commercial AC to DC charger. So we have more options for this kind of EMB. And before going to the next slide, it's important to highlight that there are many prototypes in the ongoing project and the next project. Includes the two versions of EMB and 2 types of ESD. In practice, we can select the most suitable solution based on system requirements and situational needs. For instance, we just can use the simple EMB for with the commercially available AC to DC charger. Would be enough for some system in communities. And for the next project, recently we are looking for the IoT research team to develop the IoT function or IoT feature for us, because our team is specializing in power electronics, so we are looking for the IoT team to join us to make the system can be online, and we can adjust the energy management plan online. And this slide shows the key specifications of the ESD. Both of them have rated power at 3 kilowatts, and they comply with the safety and electrical standards as listed here. The battery voltage is in the range of 30 to 70 volts, and the battery types are lead-acid and lithium-ion. And for the impact, the scientific and technological impact, the proposed conversion converter and energy management method in this project and the next project would be research topics or technical papers and patents, and for the prototypes. And for the societal, this project would improve the quality of life in communities. The current ESD are improving the quality of life and learning at the school, which has over 60 teachers and more than 900 students. This slide shows how much the energy that this prototype can save. For the system number 1 to number 5, and the last column, you can see that the green numbers are the exit energy, and the red number are the charges. So if we use this ESD, we can save money and energy. The payback time would be 1 to 2 years. For the collaborative, we have the alliance from Thailand, from university in Thailand and Japan, and we also welcome from other ASEAN countries. But the outcome would be IP, papers, and prototypes. The prototype will be upgraded to the commercial or public prototypes in the next project. For the societal output outcome is the use of the prototype in the communities. And for the collaborative, is from universities and from Thailand and Japan and ASEAN countries. Okay, I have talked about the targets of this project, and the method are about power conversion and IoT technologies. The scientific and social impact are about the IP, prototype, paper, and the use of prototypes in communities, and the proposed technology are versatile, can be applied for variety applications such as EV, charger, and renewable energy. Thank you.
Okay, thank you. We can allow for 1 to 2 questions from the floor. Are there any questions? Okay, yeah.
Okay, thank you. You are talking about the energy, what you call it, sharing. Yeah? Is it, when you are talking about energy sharing, is it up to the small power, for example? Well, just into your, no, the last picture. You just give the last picture. That's interesting.
Which one?
This one. No, the last picture.
The last one.
The last slide, yeah. You showed several houses, okay? Are you also talking about energy sharing up to that level of houses? House 1, house 2, house 3. They also can share their energy. I mean, house 1 might have more energy, the other house is smaller, have more energy than they share with their neighbors, something like that?
Yeah, they share to the neighbor system. Because in some communities, they install the independent off-grid power system separately, independently. And while some system may produce excess power and will be the waste, energy waste, because they cannot use and cannot share to others. So in this case, we just equip the ESD to share the energy between them. Yeah. So,
okay, so up to that level of houses.
This ESD also will not affect the overall system, because in the case of ESD is failure or something or malfunction, we can disconnect from the system, so the system will be able to work as usual.
Okay, thank you. Because in this case, the local regulation has to be made sure that it can be done. You see, neighbor 1 gave house 1 sell their excessive.
So
They have high excessive energy. They sell it to its neighbor. And perhaps it is allowed or not under the local regulation. Might have to be reviewed too. I mean, we do not want that people sell electricity, and if it is not legal, it may have legal impact on selling electricity, because in some countries electricity is highly regulated. Thank you.
In this case, we just apply to the school, which they can control and manage for the whole system. In the school, there are so many systems, so they just manage the energy. So they don't need to sell or to buy some energy.
Okay, thank you.
But it's very good comments. I'm thinking about this too, because in some case we need to apply this one to the communities. Maybe it's better to sell or to buy the energy from the neighbors.
It's time's up. Yeah, so thank you very much. So if you have any expertise on IoT, please feel free to talk to him. Okay, so we'll come to the next presentation. Yeah, I would like to welcome Dr. Hatyan Hafiz, from Sunway University. For the topic of IoT road health monitoring platform for secure urban mobility in smart communities.
Thank you, Chairman. Good afternoon. I'm Hadian from Sunway University, and today I'm excited to present our project titled IoT Road Health Monitoring Platform for Secure Urban Mobility in Smart Communities. This project is a collaboration with our esteemed colleagues from Sunway University, Malaysia, and also Institute Technology Bandung, Indonesia, aiming to enhance road safety and urban mobility across the ASEAN region. Let's start by looking at the background and motivation for this project, beginning with Malaysia. As of December 2022, nearly 90% of Malaysia's roads are managed by state governments. And yet, due to limited resources and labor-intensive data collection, a portion of state road remains unmonitored. This leaves many roads, especially in rural and urban areas, lacking proper health assessment, which affects timely repairs and road safety. Moreover, these issues consistently capture public attention each year, sparking calls for innovative solutions that address not only efficiency, but also public safety. The public urged the adoption of IoT and AI technologies to significantly enhance tracking and monitoring efforts, ensuring the road health monitoring and safety are prioritized for a safer community. This diagram shows the condition of Regency roads in Indonesia as of 2023. A similar challenge exists here, where a significant percentage of these roads are categorized as being in poor or severely damaged. To put this into perspective, nearly half of Indonesia's Regency roads fall into these lower categories, highlighting a critical need for better monitoring and maintenance. The focus on national roads leaves Regency and urban roads with minimal data on road quality, which delays maintenance and affects budget allocations. There is currently no established system, or at least IoT and AI-based digital system, for collecting road health data, specifically for Regency and urban networks. This lack of data leads to delays in maintenance and repair, as there is no solid information guiding these efforts. Without reliable data, authorities also struggle to justify and prioritize budget allocation for road maintenance. This highlights the importance of implementing a comprehensive data-driven monitoring system, which is essential for improving infrastructure and ensuring safer urban mobility. Now, you can see both Malaysia and Indonesia face a gap in road health data for non-national roads, impacting overall infrastructure quality. So our proposed solution leverages the IRI, or International Roughness Index, which is a global standard for assessing road health. We have three key objectives. First, to design an IoT platform for wireless IRI measurement. Second, to validate the data accuracy with a Class 1 instrument. And third, to test this platform using data collected from the community. Together, this step will enable real-time road monitoring and community engagement. The current methods for collecting road data rely on laser profilers with GPS sensor. This is what we call as Class 1 instrument. It demands significant resources, time, and manual effort. In discussion with one of the road maintenance company, we learned that they often need to travel hundreds of kilometers to collect the road data, store it in bulky hardware, and then return back to the station to transfer it for further analysis. This process is labor-intensive and time-consuming. Therefore, our solution provides major improvement by enabling real-time wireless transmission of IRI data, eliminating the need for such extensive travel. We are also integrating machine learning to predict road roughness, allowing us to cover more road networks efficiently and enhance overall monitoring capabilities. Let's take a look closer to the system design here. We have identified key requirements and designed a framework for the necessary hardware and software in collecting and transmitting road data. Our framework includes validation using Class 1 instrument to ensure accuracy, reliability, followed by a system to analyze and process crowdsourced data. This diagram shows you the outlines, the 4 key steps in our development of IoT road health monitoring platform. So step 1, start with requirement analysis. So we start with engaging with stakeholders to define the system requirements, ensuring the platform meets their needs from the start. After that, step 2 involves hardware and software development. We develop hardware with accelerometer, GPS, and Wi-Fi for communication module. And step 3 includes data collection and validation. The data is collected through mobile devices and microcontroller, processed and validated against Class 1 instrument or laser profiler data to ensure accuracy and reliability in IRI measurement. Lastly, step 4, testing with crowdsourced data. We test the platform using crowdsourced data to create IRI maps and heat maps, providing stakeholders with actionable insight into road conditions. And feedback is continuously provided to stakeholders, allowing for informed decision-making in road maintenance. So we propose a closed-loop model in here. We are seeing a promising result in our initial testing, with IRI measurements covering selected urban road conditions. We have employed a microcontroller with sensors and also GPS and a smartphone to collect the road vibration. And our current results categorize pavement condition by IRI values, from good to poor, providing a structured way to prioritize repair based on data. And this slide presents our successful mapping of road health for selected urban segments. Each road segment is assigned an RRI value, categorizing condition as good, fair, poor, or bad. The map on the right shows this condition visually. The colors indicating different levels of pavement quality. This real-time mapping allows us to quickly identify areas needing maintenance, supporting data-driven decision for road safety and efficient resource allocation. For the impact, this project has far-reaching impact as the IoT platform connects society, industry, and authorities in a unified approach. For society, it offers real-time insights into road condition, empowering community to make informed travel decisions and promoting safer urban mobility. For the road maintenance industry, it streamlines maintenance with data-driven operation, enabling more efficient resource use. And for authorities, the platform aids in effective budget allocation and align with sustainable development goals, particularly SDG number 9, 11, and 12. This slide highlights the impact of our project in 3 key areas. As in scientific area, we have proposed a new framework for road data collection, and we developed a scalable IoT platform for real-time monitoring and introduced predictive maintenance strategies. In the societal aspect, the project produced public road health datasets that can influence maintenance guidelines promoting safer infrastructure. In the collaborative side, this initiative will promote and will strengthen the partnership with authorities, industries, and academia, and open doors for cross-country ASEAN collaboration, even tech partnership to scale the platform. In conclusion, this project provides a framework for scalable real-time road health monitoring that combines IoT, data analytics, and community involvement. The outcomes include public use datasets, predictive maintenance strategies, and strengthened partnership between industry, authorities, and academia. We welcome collaboration with ASEAN countries to further enhance road safety and infrastructure across the region. We also look forward to your question and your thoughts on how we can work together. With that, I'm ending my presentation. Thank you very much for your attention.
Yeah, thank you very much. Okay, so any question from the floor?
Okay, so thank you for a nice and interesting presentation. So I have a question about the sensor deployment. So in order to monitor the road condition, like let's say for a 10-kilometer road distance, how would be the suitable amount of sensor to be deployed to make the efficient monitoring for the road condition? You get my question?
Can you repeat one more time?
Yes. So in terms of the sensor deployment, so let's say if I have a 10-kilometer long road, like how would be the amount of sensor that is suitable for effectively capture the data for monitoring and control, something like that?
Thank you very much for your question. That is an interesting question. So the suitable type of sensors, it again depends on the application, but based on our testing with the previous project, we employ accelerometer embedded in the smartphone because the accuracy is quite high here, and we can actually automatically collect the data from this smartphone. That is one way. Another way, we can also use the IoT sensors that are available, but the accuracy is also ranging from the cheap one into the expensive one. So in this case, if we want to achieve a higher accuracy, for example, with a higher sampling rate, we might have to spend more on the sensors. In this case, I'm talking about accelerometer. Does it answer your question?
So I just need to clarify a bit. So the sensor is not directly placed at the fixed location along the road, right? So it does not. Okay.
All right, thank you. So the sensor location, if we use IoT device, for example, microcontroller to control the sensor, so we put it, there are two common placement of the sensor. One is on top of the dashboard of the car, so it will record the response of the car if we move to the, for example, pothole area, so it will pick up a higher vibration, indicating higher IRI. And then if we put it, another one is put it in the sides of the wheel. This one is also common practice, but right now the trend is to put it on top of the dashboard so anyone can contributing to the data collection. Thank you.
Thank you for your presentation. Can you go back to the slide of the road condition, the really bad road condition? Go back. Okay, in this case, I think people can judge and report to some platform like that. But I think the real problem is the very slow response of the government to repair the road. So I wonder that why we need to monitor the road in the yellow area. Sometimes the government does not care the yellow case, but they will only care about the red case only. So for during the green or yellow, maybe as long as the car can run, no response from the government. And in this case, I think no sensor is required. People can judge. And another one is that I wonder about the cost when you need to drive the vehicle to survey, to measure the road condition. Is there any way to cooperate with the people to report or use the sensor to report the number, not the subjective judgment?
Thank you for your question. For first question, I do agree. It really depends on the government response. However, before the government response, currently the situation, they do not have any color that they can see whether it is green, yellow, or red. It is digitally blind. That's why we propose this initiative, so that the government can start with this platform first. Hey, you need to take attention for this yellow and red area, for example, so they can properly allocate and plan their budget. Because case study in Indonesia, a lot of Regency roads, we do not talk about a national road. National road, they prioritize it to collect the data. So there is always data for that. But for Regency road, even in urban roads, there are no currently in-place system to have a digitally visual to see the road condition. That's what we propose to the government. Thank you.
Thank you very much for raising this issue and also the problem. I am Anwar from Telkom University of Indonesia. I understand the idea of using the accelerometer, and when we have the road condition like this, and then maybe it help you to monitor the road. But in Indonesia and in some countries, we have the speed bump, or in Indonesia we call polisi tidur, or the sleeping police, yes, or sleeping policeman. So how you will differentiate where it is speed bump or when this is the real bad condition of the road? Thank you very much.
Thank you, Dr. That is an interesting question. Not only speed bump, any obstruction on the road will pick up by the accelerometer. So this is also one of the challenges for us to collect the vibration data of the road. But we need a sophisticated model, of course, that will differentiate. Normally, people will slow down when they approach a speed bump, so it will be captured in the features of the signal itself. Maybe we can use that one.
Yeah. Thank you.
Okay, yeah, so thank you very much. Okay, now we come to the last paper for this session. Yep, so please welcome Philip Bijeki.
I uploaded a video to play. Okay, I see. Okay.
Yeah, so the title of presentation is the Digital Twins, Wearable and Urban Analytics for Enhancing Walkability and Comfort in Southeast Asia. Yeah, please.
Thank you, Chair. Good afternoon, everyone. Really nice to be here. Thanks to the organizers and thanks to everyone for the nice and interesting presentations about their research. So I'm Philip Bijeki. I'm from the National University of Singapore. I'm assistant professor there. My background is in geospatial technologies, and I lead a research group in urban analytics. And in this presentation, I'd like to show you some of our ongoing research that we have conducted in collaboration with a few other research groups and also with a company from Japan, Takenaka Corporation. So this work combines multiple approaches and technologies, starting with digital twins. I think most of you might have heard about digital twins in the last few years when they have started gaining popularity. So we work on digital twins at the district and urban scale. We are working on mirroring the built environment, enabling a simulation platform to understand better urban dynamics. Then next we have wearables. Wearables have also started to be popular as a technology in the last several years. Apple Watch is one of the most prominent examples. And urban analytics is our domain in which we work on. It's the science of collecting urban data, primarily spatial data, processing such data, and unlocking new insights in the built environment that can help urban planners and designers to make informed decisions and policies. So the main background of this research is that Singapore and other cities in Southeast Asia, they are always hot, and the same cities are trying to increase walkability and bikeability. There has also been a lot of research going on in Singapore and other cities in Southeast Asia about understanding comfort. But there are multiple research gaps. For example, one of them is that exact drivers of comfort are not always fully known. It's not really known whether wind or solar exposure influences the comfort of people, and so on. Also, research on comfort is impeded by the lack of data. So there are not really data sets that people can use to support their research on comfort. And another major research gap is that comfort is way more than thermal comfort. Most people, when they hear comfort, at least in the context of Southeast Asia, first they think about thermal comfort. But comfort is beyond thermal comfort. We have also visual comfort. It's important what people see when they walk in cities. It's important what they hear as well. And in this research, we started to, in this research, we endeavored to work on understanding drivers of comfort. We have also worked on understanding different preferences of comfort. So comfort is not perceived the same way by everyone. Comfort is quite a subjective phenomenon. For example, in this room now we have a fixed temperature, but some of you may feel cold. For some of you, the temperature may be fine. For some of you, it may be hot. So the same goes for outdoor comfort. We have different so-called phenotypes of people that perceive the environment in different ways. And another goal of this research is providing monitoring and simulation capabilities. So this kind of data has never really been integrated in a digital twin. So we put together different data streams that have not integrated in a digital twin before. And the whole idea of this research is to help build better urban policies to mitigate comfort. So lots of governments, in particular in major cities in Southeast Asia, including Singapore, have been doing an amazing job to mitigate outdoor comfort and to support walkability. For example, in Singapore, the government has installed hundreds of kilometers of these walkways to shield people from the sun. This is one of the most prominent planning interventions they have done. But there have also been other interventions, such as motivating developers to install green walls and green roofs. However, more can be done, and more interventions can be supported by more information, which we try to provide. And in this research, by the way, we have already published several papers at conferences and journals, but it's still an ongoing research direction, and there are lots of opportunities, and we also see collaborations. So we started this research by joining another research group at my school at NUS in Singapore, the Building and Urban Data Science Lab, which is led by my colleague, Professor Clayton Miller. They started this research a few years ago on understanding the comfort of people inside buildings. So in this research, they have developed an app which is called the Cozy app. And this is an app that they have released open source, so anyone can download it. And it was primarily developed for Fitbits and Apple Watches. With this app, they have been collecting information about the comfort of occupants of the building of our school at NUS. So they've been collecting measures like pulse, pressure, and so on, but at the same time, they've been deploying comfort surveys that people have been nudged to answer every half hour or 1 hour, asking them how they feel. Is it too hot where they are? Is it too loud? Is it too bright? And so on. In this research, they have deployed about a few dozens of Apple Watches across students and staff over a period of a few weeks. And then they've been understanding how different people feel at different locations in the building at different times of the day. So here is a screenshot of the data they collected. The points represent the locations of people in our school, while the colors represent how people feel. For example, those points that are red indicate people who at that time feel hot. So in this research, they discover many interesting things. Like, first of all, different people feel differently at the same time, at the same place, because people have different preferences. And we like this research, and we suggested to them, why don't we expand this outdoor? So you have the technology, you develop this nice app for measuring comfort, you have the expertise. Let's step out of the buildings and let's collect data on the semi-outdoor and outdoor comfort of people. So that's what kept us busy in the last several months. We have been deploying comfort campaigns among our students. We gave them Apple Watches, and they've been walking around our campus, and we've been collecting data on how they feel. And then we thought, okay, we have all this wealth of data, but we need to connect it with the built environment, because we have to understand what are the drivers of comfort. Do people feel good walking in a particular street because they see a lot of greenery, or is it because it's windy, or is it because it's hot at that particular moment? So what we've done is we integrated all these wearable data that we have crowdsourced from our students. We have also integrated data from weather stations, so we have deployed 40 weather stations in our campus. So we know at a very high resolution and also very, very high temporal resolution what are the microclimatic conditions. And on top of that, we have also integrated information of what people see. So we collected street view imagery in the campus. So at every point in the campus, we know exactly what people see when they walk. And we run image segmentation on this to understand how much greenery people see, how much sky they see, and so on. So we put together all this data in a digital twin platform that we have developed, and the prototype of the platform looks like this. So at any point during a walking route, researchers can click on a point, on a path, and understand how people feel, together with what they see and what are the microclimatic conditions. So this is work in progress. We didn't yet work on simulations and so on, but this is one step forward to support walkability and comfort studies by putting all this data together. So let me tell you a bit more about the method, what's behind this digital twin. So we have conducted so-called thermal walks when we walk with mobile weather stations to have weather data at even higher resolution and accuracy. And together with this weather station, we also had a GoPro camera and a few other sensors to collect data along the route. Then we integrated all this data in a platform and visualize it, and all this has been relying on open source. So the app we use is open source, and the digital twin we developed is also open source. So what's the impact of this ongoing research, which we think holds a lot of potential? We think it has a lot of potential for scientific and technological advancements in developing machine learning models to predict comfort. So we collected a wealth of data, and this wealth of data can be used to develop models that predict comfort for different types of people. And it's tailored for Southeast Asia. And another impact is that we look into other types of comfort, not only thermal comfort. The research supports walkability studies. It's able to predict comfort at a detailed resolution. For example, this is the map of our campus in which we predict comfort at a high resolution. And also it's quite human-centric research because we regard different types of people and different preferences. Next, we are working on scaling this research based in Singapore to other places. We have also been successful in publications, which we want to continue with new collaborators. And also we have trained master students and PhD students in this topic. A bit more about output and outcomes. I'd like to highlight that that we initiated also collaborations with companies, for example, Takenaka and Esri, and at the moment we are growing a network of complementary research groups in our domain in Southeast Asia who want to deploy this at their own universities or cities, and we always seek new partners. So please let me conclude. Some takeaways. Some of you may be new to this topic, so I hope you also learned something new. So we think that planning for walkability is increasingly difficult, but it's quite important because it's key to resilient and sustainable cities. One problem that we are trying to solve is the lack of data that is actually helping us understand the comfort of pedestrians. Another gap that we are trying to solve is the missing local context. So we are collecting data about the built environment, not only the comfort of people, so we can relate the two to understand what are the drivers of comfort. And what I just presented is what we think is an innovative, novel method that combines different technologies like wearables, digital twins, to help disentangle different factors that drive comfort. And we think it's scalable across cities in the region. Thank you very much.
Okay, we can allow 1 to 2 questions.
So thank you very much for this. My name is Obsanu from National University of Laos. So the research is really interesting, I think. For the sensor, for the variable sensor, it's good sense to wear and monitoring all the things throughout the city. I just have one curious question that how you get the evaluation from the user? Is it have the team to go to survey or just open to the public to give the feedback from the from the feeling? This is the feeling. This feeling. This is how comfortable the people. So this is quite very hard to determine whether this is comfort or uncomfort. So thank you.
Thanks for your question and interest. So I didn't talk a lot about this in the interest of time, but basically the app that I have talked about, the open source app, has these so-called micro-surveys. And these micro-surveys, they nudge people every certain, like, depending on the context, like 1 minute or 1 hour, with a set of questions to help us understand comfort better. For example, one of the questions we have programmed is it currently too bright for you? Like, if you're indoor, are the lights too bright? Would you prefer them to be dimmer? And these micro-surveys are called micro-surveys because it takes only 10 seconds to complete them. Usually they have only 3 to 5 questions. And this is the main data stream how we sense comfort. And the best part of all is that this app, developed by my colleague Clayton Miller's research group, is open source. So anyone can change a bit the code to deploy their own questions depending on their own context. For example, if you're conducting comfort studies only outdoor, it doesn't make sense to ask questions that are more related to indoor. So far, they have deployed like 10 campaigns, and in each campaign they had their own set of questions tailored to the context.
Thank you very much.
Okay, so I think we
Thank you very much.
come to the end of the session. Yeah, so do we have a break?